Welcome back to the channel. This is the Earth Science Classroom. This video is on environmental science and atmospheric science, and in particular we are looking at photodissociation and atmospheric chemistry and what these two are and how the sun's energy plays a vital role in the chemistry and the chemical reactions involved in our atmosphere, in more detail the troposphere and the stratosphere. This is the Earth Science Classroom. Our atmosphere is a thin gaseous layer held in place around the outside of the Earth's surface through gravitational forces, and it extends up to about 100 kilometers or 60 miles up into the atmosphere, which is called the Kármán line, which is the unofficial start of space. So this really thin layer of air molecules between the surface of the Earth and space, and this thin layer is divided into four main layers. The first and closest to the surface is the troposphere, then we get the stratosphere, then the middle one is the mesosphere, and finally the highest altitude, the highest elevation layer of the atmosphere is the thermosphere, which is named based on the individual air molecules being superheated by the incoming solar radiation. And that thermosphere also includes the ionosphere, which is to do with the aurora borealis and aurora australis, the exosphere, which is basically the final layer of the atmosphere and the air molecules before the vacuum of space, and finally the magnetosphere, which is charged particles which extend out as far as 200,000 miles away from Earth's surface, which protects us from the solar winds and the dangerous energy the sun sends our way. The four main layers of the atmosphere are divided by what's called pauses based on the change of temperature trend between one atmospheric layer to the next atmospheric layer. Now, the most common gas or element in our atmosphere is nitrogen, or N2. So it's two nitrogen elements bonded by a chemical bond. And that constitutes 78% of the atmosphere. The rest is oxygen, or O2, which is two oxygen atoms chemically bonded, and that's 20.8%, and then argon, an inert gas, which is 0.9%, and the rest are called trace gases, or variable gases, like CO2, like methane, like water vapor, hydrogen, helium. All those are extremely small amounts of these elements in our atmosphere, and all those combined, there are multitude of different elements and gases in our atmosphere, and they add up to less than 1% of the atmospheric composition. So it's mostly nitrogen and oxygen, and that plays an important role in the chemistry. Both oxygen and carbon and nitrogen all are able to chemically bond with each other to create different molecules, different compounds within our atmosphere. In this video, we're looking at photodissociation, and the photo word or part refers to energy from the sun, the radiation the planet receives through the atmosphere, in particular the troposphere, and this is called sunlight. And sunlight is made up of three main components, three main types of energy based on the range of wavelength of each type. So ultraviolet has a very small wavelength, and that's about 3% of sunlight. Next is a little bit larger wavelength or range from about 400 nanometers up to around 800 nanometers, and that's visible light. That's the light we see with our eyes, from that violet, deep blue, all the way through to red like a rainbow. And then we have the longer wavelength, the less energized wavelength of infrared or heat energy, and that constitutes about half of the sunlight we receive from the Earth. So ultraviolet, visible, and infrared. Now ultraviolet is broken down further into UVA, UVB, and UVC. UVA is the larger wavelength of the three types of UV, and that is allowed through the ozone layer in the stratosphere. So we absorb and interact with about 95% of that UV being UVA. And it's very important to understand that this energy that has been received by the Earth, that's going through the atmosphere and interacting with the air molecules, is what we're talking about here with photodissociation. So photodissociation is all about the breaking down of chemical bonds between the elements and the atoms within the atmosphere, within the gases. For example, this is water vapor in the troposphere and how it reacts and absorbs the energy from the sun, the sunlight, which is called a photon, a section or piece of radiation that's going to be absorbed by this water vapor molecule, this water molecule, and it's called a quantum of light. It's a unit of energy. And what happens is this energy is absorbed into the water vapor, it becomes activated, and it goes through increased activation states, and it becomes more and more energized until the bonds between the atoms are actually going to break. So the covalent bonds, the hydrogen bonds are all going to break due to this energy being absorbed and the atom becoming more energized and more activated. That produces the breakdown of these gases in the atmosphere and produces a lot of highly reactive, highly energized free radicals, basically singular atoms or singular elements like oxygen, hydrogen, nitrogen, carbon, that are going to fly around in the atmosphere, which are broken due to the absorption of this energy, this photon. Photodissociation is a critical part of atmospheric chemistry on how these air molecules, these different compounds and even mixtures are broken down through the energized atoms breaking the different chemical bonds between the elements and forming free radicals and forming different kinds of air molecules inside our atmosphere. And it's important to understand how the sunlight is breaking down these different molecules constantly in the atmosphere when exposed to this high energy, this photon, and how these free radicals play an important part in the formation of new air molecules in our atmosphere. The production or formation of free radicals occurs when the absorption of energy breaks down these chemical bonds in the air molecules, and these singular elements, these singular molecules are going to fly through the atmosphere, which are highly reactive and unstable and energized due to the absorption of the photons, and they have unpaired electrons and they have open or available covalent bonds, which means they are extremely reactive chemically and are able to fly around and interact and bond with different molecules, different elements, different atoms, different amounts of these elements or atoms, and produce a new stable molecule in the atmosphere due to the fact this free radical was allowed to be broken down by photodissociation or photolysis and then fly through the atmosphere and then interact with a new molecule or a new atom or element. Now this happens extremely fast. They can be broken down through photodissociation and then chemically react and form new molecules within extremely quick time scale, over seconds or milliseconds, based on the concentration of different elements and atoms, based on various environments, and this is going on continuously in the atmosphere. One important free radical to discuss is the hydroxyl radical, or OH. So it contains a single oxygen atom and a single hydrogen atom. Now this comes from the breakdown or photodissociation or photolysis of both ozone, which is O3, and water, which is H2O. So you're basically releasing the single oxygens from ozone and water and combining with the single hydrogen to create this hydroxyl radical. Now this is very energized, unstable, and able to chemically react with many other air molecules and atoms and elements already present in our atmosphere, like nitrogen and carbon, and again, more ozone or more water. Now, these are very short-lived chemical reactions, and it's based on the concentrations of both water and ozone in that given area of the atmosphere. And hydroxyl radicals play an important role in the chemistry of our atmosphere. In conclusion, photodissociation is the absorption of energy from the sun, called a photon, by air molecules present in our atmosphere, mostly the troposphere and stratosphere. Air molecules such as nitrogen, oxygen, CO2, argon, water vapor, methane, all these different types of air molecules absorbing the different kinds of energy based on their wavelength, mostly visible light, infrared, and some ultraviolet, and this is going to break down the chemical bonds between the air molecules, creating singular, energized, chemically reactive free radicals, which will move through the atmosphere, through the different elements and atoms, chemically bond and create new air molecules to constantly adapt and evolve our atmosphere on a second-by-second basis, whereby air molecules are broken down and then reformed and chemically bonded to make new air molecules within our atmosphere. This is the Earth Science Classroom. Thanks for watching the video. If you liked it, please subscribe, like, and share. And if you want more content and videos on Earth Science, please check out my channel.